Okay. So, I start at the point where I left yesterday, that is, if you see this weight update part in the Bloch-Lewis algorithm, sorry, this is R, right, R is 0 to this for the real case. You know what change will be there in the complex case? In the complex case, this data vector will be as it is, there will be a star across, I mean on E, and in the filter part it will be W transpose x n, W transpose I by W Hermitian I times x n. Okay. That was the only difference. Okay. We will extend this to complex case as well. I think that extension you can do easily from real to complex version of Bloch-Lewis algorithm. That is not difficult. That LMS case we have seen how it is, it will be so. Anyway, let us see how this can be done. Before that, remember one thing, yesterday there is a filtering part also. If I write the entire algorithm, y I L plus R was what? W transpose I x I L plus R, and then you calculate E I L plus R as, this is pretty simple, minus y I L plus R, isn't it? I am not writing the full algorithm that for r equal to 0 to L minus 1 if you want, for r equal to 0 to L minus 1, this is one loop, this will be outer loop, this is on I, this part of it. Okay. Remember one thing, what we discussed yesterday, in the filtering part, we will follow overlap and save. In the overlap and save, what do we do? How will the blocks then be formed? That is, we have to discuss that first. Suppose this is a block of length L. Then, and what is the filter length? Filter length is capital N. So, I will take, this is a 0th block, length L. I will start the next block here, somewhere here. Okay. So, that there is an overlap of n minus 1 samples. This will be my next block first. Next block will be here, dot dot dot, so and okay. So, that means earlier it was 0 to L minus 1 and the next would have started at L. Now, it is starting at n minus 1 to the left of L, and then it is going up to L. So, L plus n minus 1, so new length is L plus n minus 1. Okay. For the first block you can assume some zeros here, because its length is L, nothing, no overlap portion, zeros here, that is okay. Okay. But for all intermediate blocks, length is L plus n minus 1, you can call that capital M. Okay. So, earlier it was length L, now m minus 1 zeros, L plus, I mean length M. Then again it was starting here going up to L, I am appending n minus 1 data from the last n minus 1 data here. Then here also it was to start at what, 2 L, but now it is, I am taking a last n minus 1 data, from here it goes up to this. Okay. So on and so forth. I will be using say that way dot 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 for the ith case, this is I L and I am having extra n minus 1 points, and it will go up to I L plus L minus 1. This is my ith block. For this block I will be using W I as the filter. Okay, W I as the filter, I will be using convolution at this point, this point, this point. When you convolve with this point or this point or this point or even here, I get this data from the past. Okay. When I am here, it is assuming some 0 values, but in practice, in real life, there is data from the previous block we have discussed yesterday. So, at all these points I get wrong result only from n minus 1th point, this is 0 to n minus 2, total number is n minus 1. So, this is n minus 1th point from counting from here. From that point onwards only I get correct result. So, I will hold that result, throw away this result. But before that I have to do the filtering, isn't it? For the filtering part, what I have to do? I am interested in filtering here, all these points, that is this equation. But if I have to do by circular convolution and all that, if I have to use a 50, I use this part and all these parts, and I will be using circular convolution by DFT. At all these points, whatever comes, I will throw that away. Firstly, that is wrong. That is not even linear convolution. If just this block and the filter block was giving the linear convolution, result will not come at these points. And even otherwise, if they are correct, in the context of the entire data stream, these are not correct, because it is assuming 0 to the left, whereas this is just part of the continuous data stream. So, the real convolution data to the left of this point would have come in. So, I would have thrown away. So, I would get convolution output here, and that is what mathematically is this. Convolution starts at IL plus 0, IL plus 1, start at IL plus 0, then IL plus 1, IL plus 2, all these points, convolution output. Okay. So, my current filter length is, my data length is not L, but L plus n minus 1, which is m. Okay. So, filtering part is all right. If it is complex valued filter coefficients, instead of W transpose, it will become W Hermitian. Note that change also. Okay. Is that understood, Javjit? Okay. Now, come to the weight update part. In the weight update part, see the data structure. Put r equal to 0. I will draw it separately on a page, but just here you see the data structure IL. IL means ILth point and IL minus 1, IL minus 2 up to these fellows also, the same points. There is a data vector at this point will consist of data up to these. Then IL plus 1 means you are going to the next guy. So, data up to 1 less from here, okay, so on and so forth. So, remember in this weight update part, what are the data samples involved? The data samples present in this block. First, how? Because in XIL vector, I take this entire vector and then this point, and progressively I go to the right. Okay. So, that means both for weight update and all, this one chunk of data, one block of data is enough for me. In the filtering part, I will do a circular convolution by FFT, but I will throw away the first n minus 1 samples. Then from ILth point onwards, circular convolution wise also I will get the correct result as given by this equation, isn't it? This is the convolution, but IL plus 0, IL plus 1 at those points. Okay. And in the weight update part, I will now show you how to do. So, please see the things. You have got one sequence, say E, in this sequence, suppose this point is IL. So, at this point you have got EIL, dot up to say EIL plus L minus 1, and suppose I have 0, 0, 0, dot 0. What is the, how many zeros? N minus 1 zeros I put. Okay. I put n minus 1 zeros. So, what is the length of this vector? L plus n minus 1, that is m, capital M, same as that data vector. Okay. And remember, in the weight update part, if you see the weight update equation, put r equal to 0. Okay. For your convenience, I have to draw this way. EIL, this is a separate story. EIL is multiplying what? X I L vector. What is X I L vector? X I L minus 1 dot dot dot. This is this tail part, this part I L minus n minus 1. Okay. Then E I L plus 1. This is multiplying, this is multiplying, this is multiplying this vector. This is going one further, this is coming down like this. You can see this down, this kind of diagonal movement. Dot dot dot, here it will be again one less, dot dot dot. Finally, E I L plus L minus 1, last fellow will be multiplying whom? Is this portion visible in the screen? Is this visible? What no? Either yes or no? Okay. Dot 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 dot. Okay. So, I will be multiplying these vectors by those E values and then add, that is the theory, and then I will get a resulting vector. That is what I have to do in the weight update computation, that is my main job. First, I am considering only the first entry of that resulting vector. How will that come? E I L into X I L, E I L plus 1 into X I L plus 1 dot 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 added. Next will be E I L into X I L minus 1, E I L plus 1 into X I L dot 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 added. So, that means, if I graphically see E I L here, suppose here again I have my X I L, because this is I Lth point, then I have got and those data x minus here it is x I L minus 1. Are you finding? Is it okay? Can you understand what I draw? Yes. And now suppose this I just multiply sample wise. These zeros will multiply this past value, isn't it? Only E I L into X I L, from then onwards I will get E I L X I L, E I L plus 1 into X I L plus 1, this is E I L plus 1, this is X I L plus 1 dot 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 up to this. So, I will get the first entry. Then if I shift this to the right by 1 and let any garbage come from behind, but if I shift by 1 and then again do sample wise multiplication, these zeros will take care of the same portion of n minus 1 length data. E I L will multiply X I L minus 1, isn't it? And this guy will go out, next fellow will come. So, I will get the second entry, isn't it? Second entry, then I shift it further again, let any garbage come. So, I will go on shifting how many times? Just n times. 0 shift, 1 shift up to n minus 1 shift. After n minus 1 shift, this fellow, this guy will come below this E I L. Okay. So, E I L into this. Total n, 0 shift, 1 shift, n minus 1 shift. 0 shift, this guy is at the 0th position, first shift is the first position, n minus 1th shift at the n minus 1th position. N minus 1, this is n minus 2, because length is n minus 1. So, this is n minus 1th position. Okay. Fine. After that, I do not shift, or if I go on shifting and do this business, I will ignore those results, I do not need them, isn't it. So, you remember that this is something what we do in circular convolution. What do we do in circular convolution? One sequence I hold as it is, other sequence I make a periodic version, reverse, I shift and chop off the right and left and sample wise multiplication. So, that means what I see with 0 shift, this is a 0 shift case, but after reversal, then that is why if you multiply sample wise you get the first entry of the vector, isn't it. So, that means after reversal 0 shift is this vector, this sequence, that means already 0 shift. So, what is the original sequence? I have to reverse it this direction, I will get a portion on the left, make a periodic version, bring it here and then see it only in this window, isn't it? It is simple engineering, nothing else. Those who do not understand, they do not deserve to understand. It is very simple. I will reverse it, because this is a reverse version. To go to that, I will reverse it. This portion will go to that side. Now, using periodicity, this is a periodic thing. This whole thing will be periodically repeating. So, I will get one chunk in this. I will just separate out, forget about right and left. That is my original sequence. If you proceed for circular convolution, you will get this. That is, make a periodic version, reverse it, then without shift, whatever see in the window, multiply, you get the first entry, then shift it once. In the circular convolution, you go on shifting even beyond the n minus 1 shifts, because you have to complete the entire thing, but I will ignore those results, I do not need them. All right. That means, originally what is the sequence? X here, this as it is. Can you tell me, if you reverse it, what will be before this? This guy will go, this is, yes, I L plus L minus 1. So, I am not showing that, but if I have to really do like a school level teaching, I would reverse it, I will take it to the left hand side, identify each sample, then make a periodic version of that, see what comes here, then only take that out. Those intermediate steps I am not going into, I am asking you to imagine. Are you understanding? If you flip it to this side, this fellow will be the starting guy, and then progressively, if you flip it, I L minus within bracket n minus 1, next is within bracket n minus 2, n minus 3. So, this will be I L minus n minus 2. Okay, this remains as it is. Next guy, from this guy onwards is flipped. So, this was the rightmost neighbor, I mean the adjacent guy to the right, this will be the adjacent guy to the left. Next adjacent guy here, next to the left, like that, that way. And the entire thing will be pushed back here. Okay. Then my claim is, if you use this, if you have a circular convolution between this sequence and this sequence, whatever be the output, output is over this length, but there you take only the first n minus first n, 0 to n minus 1. After that, you whatever result you get, forget that. Okay. Then you will get that weight update thing. Is it understood, or you want me to repeat? I do not mind repeating this part. Do you need some clarification here? To him, is it understood or not? You can easily check now. I flip it, and then I make periodic version of it, reverse. Whatever you see on the left hand side, that will come here. This guy will remain as it is. This will come to the left hand side. Okay. So, that is again by periodicity coming here, I L minus within bracket n minus 2. So, here it was n minus 1, n minus 2, that way. This was the rightmost neighbor, I mean the right neighbor, immediate right neighbor, this will be the left neighbor, okay, and that will come here. All right. So, that means I have to do a circular convolution between the two. What is the DFT of this? Okay, I can take the DFT. You give me the E sequence, error sequence, I added some extra 0, maybe make it a bigger vector of length capital M. I can take an M point DFT of that. But how about this guy? It has got some extra data. Earlier I was living happily with L point data vector. Now, some extra garbage has come and they have kind of got flipped and order has been changed and all that, isn't it? So, what do we do to that? That is the question. Now, I show you some beautiful property of DFT. Suppose now this is a separate story. Even if I use capital N symbol here, that is not the N there. Okay. I show some property of DFT, since I was using capital N there, I was using capital N. That is not the N used in that filter length of adaptive block adaptive filter. Okay. I am showing a separate property of DFT. Suppose you are giving x k for any length capital N sequence x k, DFT k equal to 0 1 dot 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 n minus 1. original x n was, if you put it in a vector form, x 0 x 1 dot dot, you are taking the DFT. Now, I tell you, look, I want to play around with these coefficients. I will take a conjugate of them and then take inverse DFT. I will get another sequence. How is that sequence related to x n? Not exactly, it's okay. Suppose I take x star k and I take IDFT of that, then what will I get? So, fine, I take IDFT formula I know. This plus here now. IDFT at a particular index, time index of your choice small n within the range small n equal to 0 to small n equal to capital N minus 1. The time index fixed. This is a quantity. If there are no star, I know this would give me x of n, small x within bracket small n, but there is a star here, so problem. So, let me do some mathematical manipulations here. I bring back the star here, no problem, and e to the power minus j 2 pi, but in the DFT there is a e to the power plus term, not minus. So, what I will do, I can write like this. It was minus firstly. Okay, for your sake, let me do it 2 steps. Okay. Before I proceed further, this is summation over this your n minus 1. For n equal to 0, what is this sum? E to the power 0 1. So, whether it is plus sign or minus sign does not matter. So, what you get is x of n only, x of n, because there also n was 0 and e to the power 0 1, x of n, there is x of 0 because n is 0, conjugate of that. So, n equal to 0, this leads to x star 0, and for n not equal to 0, there is a problem, because I really have to, I cannot, this is present with a minus sign, otherwise it become 1 independent of whether it is minus or plus. Now, that phenomenon goes. So, then I apply a simple trick. I add j 2 pi into capital N by capital N into k, e to the power j 2 pi into k, there is always 1, and that k I am writing capital N by capital N into k. Here n equal to 1 to up to n minus 1 and a star. So, n equal to 1 means capital N minus 1, n equal to 2 means n minus 2 dot dot dot, n equal to capital N minus 1 means 1, and this is what x of. So, this gives rise to x of. So, what is the sequence? Sequence is very simple. The inverse DFT, if I put a vector form, original vector was this, now it will be starting guy will be x 0, there will be a star I am putting outside. For the time being, I will be dealing with real valued things. Okay, so, x 0, the data star for our case will be x 0 only to start with. Then it will be that means, if I have this sequence, if I take its DFT, it will be x k star. I went this way, but relation is 1 to 1 and unique. So, that means, if I take this guy and take his DFT, I will get back x star k. Okay. Now, come to this. So, look at this thing, 0th guy remains as it is, but the last is just flipped. This is just flipped, n minus 1 goes to 1 and 1 goes to this. You understand the flipping, na? If you just flip it and then push it back so that it fits here. Hmm? No circular shift, by the way, this is a simple flipping. X 1, 2, 3, 3. So, 1 goes here, it goes in the opposite direction. 1, 2, 3. It was coming down like this, coming 1, 2, 3, 4 like that. Now, it will go up 1, 2, 3, 4 like that, but only up to this last but one position or first but one position. Okay. Now, come to this guy. This is a sequence with whom I have to do circular convolution. Then only periodic version, repetition, and then you see this part and you get that sample wise multiplication, immediately you get the weight update formula, isn't it? So, this is the sequence with whom I have to carry out circular convolution between, with this guy on whom I have to carry out this. Okay. That means, in DFT domain, DFT of this into DFT of this. DFT of this is okay. Error samples I put, identity of 0 vector, take a DFT. This have to compute. But here, if you ask me again to compute a DFT again for this vector, it is more computation, but I am saying no. Okay. Look at this thing. If you consider this to be the starting guy, here also same, but otherwise there is a flipping, isn't it? This fellow was the last, it came here, and this fellow was this I L minus within bracket n minus 2 here, this has gone here. Okay. Since I am dealing with real case, there is no star. So, if I take star and say star is useless, but still you can put star. Then if I take a DFT, I will get x star k, where x k is the DFT of what? This basic vector, simple block, these blocks. Take a block, and where do I need this DFT? In the filtering part, overlap and save method. Same DFT, I do not have to recompute the DFT of this reordered vector. I computed DFT only once here. That is how I am saying how the computational gains come. Otherwise, one more DFT would have been required, isn't it? This I need, because I am doing the overlap save method of filtering. So, the circular convolution thing was there, and throw away the first n minus 1 sample output and all that, add zeros. This filter vector is length n, and this is L m. So, add those difference of zeros and then circular convolution. That we did yesterday, now overlap and save method. Filter length was less, capital N here, and this total length is what? Capital M. So, you have to have extra zeros. Then if you do circular convolution and throw away the first n minus 1 samples, you get the correct output, isn't it? So, that time I need circular convolution means what? I will be doing in frequency domain DFT and then finally inverse DFT, DFT into DFT, then inverse DFT of that. So, I have already computed the DFT, this DFT once. Now, claim is here to compute the DFT of this vector, I do not need to recompute the DFT of this guy. Earlier I got x k, capital S k, now it is simply x star k. Okay. So, then it amounts to a very simple thing. Let me draw the block. How will you do this business? The input x n is coming, you do this initial part serial to parallel. Okay. Serial to parallel and then buffer. Buffer length here is equal to L plus n minus 1 equal to m. The meaning of this buffer is, you see, you are taking this data, making it parallel. Actually, it is one should not use this serial to parallel, because serial to parallel you use in the context of binary bits. This serial to parallel, I do not know why he adds it should not be there according to me, because you just simply store the data in a buffer. So, you can ignore this straight goes in the buffer. How many data I am taking? L. Also I am storing the last n minus 1 data of the previous block. So, I am forming a bigger vector here. Okay. Then first thing is I will be taking FFT of that. How many point? M point. M point. For the filtering part, what will you do? For this block, I took the DFT of this. Are you okay? And filter weight, suppose I know the filter weight has been updated, I know the filter weight for this block, ith block, Wi is known. How we do the convolution? Wi here, and then you have 0, 0, 0, 0, 0, isn't it? Then two lengths are equal, then do circular convolution, ignore the first n minus 1, remaining ones are correct. So, that means what I have to do? This FFT I have found out. If I know this FFT, suppose by hook or crook I know this vector and its FFT is known somewhere, then the two DFTs will be multiplied and I have to take inverse DFT, ignore the first n minus 1 sample. That is the filtering part. So, suppose this is I do this way. Xk is here, Xk here also. Suppose I know the Wk, and this Wk means after appending zeros, you take the vector, then take its DFT, that DFT is Wk. Suppose I knew that. So, I will do that, and then I have to take I DFT of that. I have written on M point FFT only once. I hope you understand that everywhere when I write DFT or IDFT, it will be M point. In fact, instead of FFT, you can call it DFT also, because I am writing IFF instead of IFFT, I am writing IDFT. So, in case you are confused, DFT, but basically you will be using fast algorithms only to implement them, okay, not just primitive computation. After this IDFT, you ignore I am writing this way, book write something else, ignore first n minus 1 terms. Okay. So, filter output is available. Here filter output is available from this point IL to this point. Filter output is available here. You ignore those terms, first n minus 1 terms. On the weight update side, what I said, same xk I can use, but I have to use a conjugate of that. Then only it amounts to what? DFT of this vector, which is flipped, except for the first element, everything is flipped, and assuming a conjugate, but there is no real data, so conjugate has no meaning. For that, if you take the DFT, it is nothing but x star k. So, I simply take x star k times, that is the circular convolution between this and this error sequence, which is 0 here. If you carry that out and take only first n cases, rest will be garbage will come and some garbage will go into and sample wise multiple error, but I do not need them. So, take only the first n, then I will get that weight update, that update term in the weight update formula. That means, here I conjugate. Actually, this weight has come. So, after ignoring first term, you get a actually vector parallel form. So, you can assume. So, this is the output. You can take out here out, but also I have to find out now error vector error. So, sorry, this is minus, this is plus dn minus yn, that is the error, isn't it? Yn output is coming in a parallel form, in a kind of a total vector has come out. So, dn also If I write S by P, I only mean buffering, not that is d of I L plus 1, d of I L plus 2 dot 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 d of I L plus L minus 1. So, this error, so I get an error sequence, which kind of error sequence? From EIL to this. I have to now add extra zeros. How many n minus 1 zeros in the beginning? So, add n minus 1 zeros in the front. So, again length is L plus n minus 1 equal to m here, this is m point. Now, you take the DFT of that, the two DFTs are to be multiplied. There will be a multiplication by mu also somewhere. Okay, mu I will do later. Two things multiplied and then IDFT. So, by IDFT, what do you get? Circular convolution between the two. But I told you between the two, I will return only the first n ones, remaining ones I will put say zeros. Why 0? You will see. Why 0? Because my weight update formula is all these are length L, sorry length n, isn't it? But remember, in that circular convolution, filter, I mean I added n minus, I added extra zeros, isn't it? How many? L minus 1 zeros. Total length is L plus n minus 1, length n. So, L minus 1 zeros I added. Then only I took his DFT, that DFT I used in the filtering part. So, this vector I will add here extra zeros to all of them. Here 0 0 0 I will add here also, 0 0 0 here also I will get therefore 0 0 0. Are you following what I am saying? This notation, this vector as it is, length n, I will have L minus 1 0, L minus 1 0 here, L minus 1 0 in the bottom. If you add them naturally here also in the last L minus 1 positions will be 0. That suits me, because if I take that DFT of that can be used in the filtering part in the circular convolution, because there it was needed that last n minus L minus 1 guys should be 0. Okay, see how beautiful this thing is, things are fitting in all things, no, all directions. So, in the weight update part, then to carry out this, I told you that I will take circular convolution between this and this, but I need only the first 10, remaining ones I do not need, but I put in zeros there. So, that this 0 vector comes below. And suppose the previous block, the weights are been updated like that, the last L minus 1 guys are 0. So, if you add, if you do the update, this also will have 0, isn't it? Now, DFT of this is DFT of this plus DFT of this, isn't it? But DFT of this means what? This, sorry, yes, that is correct. So, what I will do, let me first of all write down, I am making one mistake. Let me first write down this, the make last how many points? No, L minus 1. In this figure I would explain that, what I was explaining. Yes. So, I got this term, you see, I got this term, I did the circular convolution. How? by the two DFT and then IDFT. I got the circular between the two, but there I am saying in time domain I do not use, I use only first n points, afterwards other terms are no use and I do not use, but then I am deliberately putting zeros there, I am putting zeros. Then I am taking DFT of this. So, DFT of this plus DFT of this is the DFT of the next future weight vector, is not it? So, the future weight vector, so there will be a loop now. This is again schematic, this is this delay, actually it is a block delay, not one sample delay, it is a block delay, because filter weights are held constant over a block. So, it is a block delay. How to draw this? Actually, this is space is too less, it is becoming very clumsy. Somewhere I should have a multiplication by mu. Maybe earlier only, here only you do multiplication by mu. My drawing is a bit clumsy, please excuse for this, I am trying to derive space. What I am doing is current weight, this k means, mind you, this k is the DFT index k, this W actually for the ith block, there should have been an I index here, but in this figure in order to avoid complications and not to bring in so many symbols, I avoided, but here everything is with respect to the ith block. So, the W that is shown is ith. So, k only indicates it is the FFT domain. So, FFT of this for the ith block, that there is a current one which is used for filtering part, in the filtering part, that plus this update term DFT of this entire stuff has come from here, they are added, held back for future use. After a block delay only it will appear here. Okay. This is the first algorithm. You see how, I mean, by cleverly using the data structure and all, we have reduced the total number of DFT operations. If it were a complex case, still this will work fine. In the complex case, what we have? We have W Hermitian I L plus R, this kind of thing, isn't it? For r equal to 0, r equal to 1, r equal to 2. Okay. That is one thing in the filtering part, that was the term, and in the weight update part term, it is x I L plus R, E star I L plus R. These terms would have come. Plus this, isn't it? But suppose, since in the filtering part you are not taking Wi, but you are taking the W Hermitian, means basically column vector to row vector, but actually conjugate of each element is used. Suppose in the weight update itself I take the conjugate, this time domain operation. In the weight update itself I am interested in this, because instead of finding out Wi plus 1 and then taking the conjugate, let us update the conjugates only. Suppose I do that. So, that means this is star and this star will go, this will come here. Okay. Now, you remember one thing I told you, that this property said what, that it will be, there will be a star here, then I said it is a real value. So, star has no meaning, but when this is complex, then the star comes in, is not it? Data vector has the star. So, that means in all these convolutions, there will be a star everywhere on the data, star, star, star. So, that means data conjugate and then this flipped version. With the star and flipped version, if you take DFT, then you get x star k. Earlier I bypassed that, saying that why data is real. So, conjugating data has no meaning, so it is okay. but actually when data is complex, you remember I proved it, na? I proved it that if it is x star k, the corresponding data vector is not just flipped version, there is a conjugate sign also. That time I took real data, so I found this has no use. But in actual case, when this is complex, there is a conjugate here. There is a conjugate here, and again there is no problem, because in the weight update formula, if I put a star here already, data becomes conjugated. So, that means in all these circular convolutions, after flipping and all, star already comes in. So, again I can take x star k to represent the DFT of this, isn't it? So, then that times this fellow will be what? Will be already, it will represent the DFT of the W Hermitian vector, that is DFT of this side, left hand side. Conjugate was already there, DFT of that. That DFT and this DFT, circular convolution and IDFT, it will correspond to the correct linear convolution with W Hermitian, this thing. Okay. And this W Hermitian comes back, and therefore, mu into this part should come, but that is coming because of this conjugate times this and IDFT. I told you that amounts to what? Circular convolution between the two with a star here. Okay, so, this part comes here and added and held back. Okay. This is a very exciting result. And that is why I did it. This is very, it shows how, how this is the elegance of DSP, how things fit into each other, and I mean, you can reduce complications, computational complications. Is this understood? Well, actually after this, we have exam, I know, but after this what I have to start is again mathematically very exciting. It is a new topic, there is a new approach to adaptive filtering. It is a more general, very fundamental approach, and I would say very exciting, because that algebra is really great. That is vector space treatment. So, I do not know how much vector space you know, but I will be covering some good deal of linear vector space called actually Hilbert space here. I will go up to orthogonal decomposition of subspaces and all that, okay. And all that will be in the context of, towards the end, in the context of Hilbert space of random variables. And then this again will take a relook into this adaptive filtering, optimal filtering as orthogonal projection. I already mentioned that, but that was using some analogy in the 3D world, but now this time will be rigorous. From that onwards, I will be building up some other kind of adaptive filters using that framework, that Hilbert space framework. One of them is a lattice filter. Lattice filter has the advantage that I mean, here you have got order fixed. Filter length has either n, capital N weights, capital N number of weights. If you have to see how the filter performance would be if I had used n plus 2 or n plus 3 number of taps, you have to again redone the LMS algorithm and all that. But lattice is one thing which is order recursive. These are only time recursive from Wn to Wn plus 1, recursive in time. Lattice filter, adaptive lattice I am talking about, it is recursive both in, ordinary lattice is recursive only in order, non-adaptive lattice. A lattice filter actually is one realization of FIR filter. Okay, forget about adaptive lattice. Suppose I have got FIR filter, low pass filter or high pass filter, fifth order. So, you have got a fifth order lattice also. Fifth order low pass filter means fifth order lattice. Suppose you want to say that, look, if I had designed a sixth order low pass filter, how good would it have been? Then you have to again redesign, destroy those 5 coefficients you used earlier, you have to redesign and you get new 6 values, isn't it? And you see this. But in the case of lattice, it permits you to retain those 5, I mean fifth order lattice means actually is a cascade of 5 basic stages. There is a basic fundamental lattice stage, you just cascade it 5 times, you get fifth order. So, to move into sixth order, you do not have to destroy those 5, you just cascade one more, another one. So, together it will be a sixth order. So, you can tap at the first, you can tap at the second, third, fourth, fifth, everywhere you see first order performance, second order performance, third order performance, fourth order performance simultaneously. That is the beauty of lattice filter. Now, the lattice filter like FIR filter can be non-adaptive, then can be adaptive, and why it should be adaptive we have already explained. Similarly, lattice can be non-adaptive, non-adaptive I am not considering, but it can be adaptive also. Okay. So, I will basically march towards adaptive lattice, but there is another reason, another very what to say sound application of lattice filters, that is in the case of speech processing. Do you know this autoregressive movie modeling, AR process, AR modeling in time series modeling? Some of you may know, some of you may not, which is useful in power spectrum estimation also. There is one kind of model called autoregressive model. It is a model that has a transfer function with only poles and no zeros. So, its transfer function will be like this: if y n is output and input is x n, it will be y n only pole, no zero. So, y n plus maybe a 1 into y n minus 1 plus a 2 into y n minus 2 plus dot 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 a p into y n minus p, okay, a p into y n minus p equal to some x n. This has no zero, only pole. These kind of models are called autoregressive models, all pole model. It can be shown that many random processes, most of the random processes can be modeled as though they are generated by driving a model like this with a white noise. These are all very good statistical theory and all that. Okay. Similarly, you can have a defined models also, moving average model, where it is only 0, y n is some b 0 x n plus b 1, that is a FIR filter, b 0 x n plus b 1 x n minus 1 dot 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 b q x n minus q, only 0, all 0 model called MA model, moving average model, and there can be the normal pole 0 model called ARMA model, autoregressive moving average model. Now, ARMA and MA we are not particularly excited because the corresponding equations are non-linear, non-linear, because the input is not known, that white noise samples are not known. So, if it is b 0 into x n, b 1 into x n minus 1, b 0, b 1 model parameters are to be identified. So, we do not know them, and input x n minus 1 drive white noise samples, they are not known. So, product of two unknown, it makes it non-linear, all the algorithms go haywire and it is all very approximate and all. But in the case of AR, y n times a 1 or y n minus 1 times a 1, y n is the filter output, which is the data I am receiving, I am modeling that. So, those samples are known to me, is not it? So, that is why here it is a linear problem, it leads to beautiful fast algorithms and all, and very good properties. This is used for modeling many random processes, and particularly speech. Human, it has been established also, the way we generate speak, actually in our voice box here, there is an AR model, AR process, actually there is a filter. It is its parameters change, number of poles, again pole location, everything change, it is excited by a white noise produced by us, and corresponding random process is generated, which gives rise to some sound or other. Okay. So, for all speech modeling, speech characterization, compression and all, this AR modeling is very useful. You know this LPC, linear predictive coding, this is related to linear prediction, these coefficients are identified by linear prediction. The entire thing is to identify the model. This is all related to AR model, is related to lattice filters. 0th order model, first order model, second order model, third order model, similarly 0th order lattice, first order lattice, second order, it leads to a lattice filter. So, for the next class, I will get into this more, I will not say rigorous, but or maybe rigorous is the word, is mathematical treatment using there will be nothing analogous, nothing based on analogy on everything, I mean based on sound logic, but again without requiring any advanced maths and all. I will spend quite a few lectures on this Hilbert space treatment. Vector space treatment, vector space with a dot product is called a Hilbert space. Dot product is something we call inner product actually. So, that will spend on this. From then onwards, after that I will go into lattice, because there are other ways of deriving lattice, but I do not like that, because mine is a unified treatment. When you go to recursive least squares, not only LMS, recursive least squares kind of adaptive filter, same approach can be used there, projection based, orthogonal projection based approach. Okay. So, that is all, and good luck for your midsem. Have to set your paper. Thank you very much.